Up until this point in the course, we have acquired a very solid and useful set of skills for manipulating data, but we haven't talked at all about how to visualize them. So in this particular lesson, we're going to finally take a first look at how to produce graphics using R and the tidyverse. So, when we produce graphics for a scientific purpose, the number one thing that we want to go for is clarity. The plot should make it obvious what it is that is being plotted, what the different axes represent, what things like the colors, shapes and sizes of, say, points or lines on the graph actually mean, and what the overall message of the graph is. So in this lesson, we're going to be learning how to create publication quality figures, and also learn how to do that using the general principles behind what is called the grammar of graphics. So let's just go into what that is a little bit right now. So the grammar of graphics is a relatively recent idea that was proposed by Leland Wilkinson in a book published in 2006. And the idea is that just like ordinary sentences in human language have various fixed grammatical parts, like there has to be a noun, there has to be a verb, those have to be connected in some way, etc. In the same way, scientific graphs also have fixed parts that have to be combined in some way, and specifying these fixed parts is what actually defines the plot. The grand idea behind doing this is that one should not have to change the underlying data in order to display it in, visually speaking, vastly different formats. In case you have worked with different kind of plotting software before in your life, you will know that very often you have to change the format of the underlying data in order to plot it in different ways. That is not the case when working with the grammar of graphics. You do not need to change the underlying data. Actually, that needs a little bit of a qualification. Yes, you do not need to change how the underlying data are organized, as long as those data are in tidy format. So this is another important place where the concept of tidy data comes in. Yes, it is true that we do not need to manipulate the data further in order to plot it in different ways using the grammar of graphics, but in order for that to be true, the data have to be in tidy format. By now in the course, we know exactly how to put data in tidy format, so you have all the tools to do that. In other words, when plotting some data, those data have to be already in that tidy form. In order to be able to use the grammar of graphics, we need to load the tidyverse as usual, and just pointing out that it is this package, the ggplot2 package, which implements the grammar of graphics, and that is in fact the double G at the beginning of the word. Let me highlight that, there we go. The GG in ggplot2 stands for grammar of graphics. So again, just to review where we are, we've already talked about the dplyr package. That's the one that contains things like select, mutate, filter, and so on. Now we're going to be talking about the ggplot2 package. We've already talked about the reader package, read delim, read tsv, read csv, and so on. We've talked about the tibble package, which has tibble, tribble, and all the support for tibbles in general, and the tidyr package, which has functions like pivot longer, pivot wider, and separate. But today we're going to be focusing on ggplot2. As per usual, we are going to be using the Galapagos land snail dataset, so we load it and we are going to be using it in subsequent examples. So let us finally take a look at the anatomy of an actual ggplot object. It always starts with the function ggplot, and ggplot is a function that takes two important arguments. The first of these, as with essentially any of the tidyverse functions, is the actual tibble that we want to plot from. So that is the data argument to ggplot. Of course, only defining the data that we want to plot from doesn't tell anything to the computer about what we want to plot. Therefore, if we were to run this line in R, all we would see is an empty canvas. In order to see something a tad more interesting, we have to add the next argument to the ggplot function, which is called mapping. And mapping is actually short for aesthetic mapping, and I'm going to explain what aesthetic mappings are. So, an aesthetic mapping is always defined by this weird helper function called AES. Again, that is short for aesthetics or aesthetic mappings. The aesthetic mappings are all of those properties of a graph that are being controlled by the data. Therefore, their structure is as follows. They take in as inputs some property of the graph, such as what should go along the x-axis and what should go along the y-axis, and that is why in the AES function you see that there is an x equals input and a y equals input. X is the aesthetic mapping that controls what goes along the x-axis, and y is the aesthetic mapping that controls what goes along the y-axis. In this particular case, what we're telling the computer is that we want the size column from the snail's dataset to define what goes along the x-axis, the horizontal axis. And we want to use the shape column of the snail's dataset to define what goes along the y-axis. Alright, so there's at least something a bit more interesting on this graph now. Namely, there are axes labels, so we see that the x-axis is labeled size and the y-axis is labeled shape. Those are the names of the columns that the data for those aesthetics come from. And you can see that tick marks have automatically been also added to this graph. You can see that the sizes are in the range of a few dozens maybe at most. And shape varies from about -0.1 to 0.1, maybe a bit more. So this is still not a complete graph, of course, but before moving on, let me just mention that most often the form in which we would call this kind of function, the ggplot function, is a little bit different. Namely, most usually we would pipe in the data to the ggplot function, and most often we would not write out mapping equals AES, etc., simply because that argument to the ggplot function is always the same, so there's not much point in naming it. So applying a little bit of shorthand, this is the most common way of rewriting it. This is exactly the same as before. We pipe in the snail's data into the ggplot, which then therefore becomes its first argument, which is the data. And then the second argument of ggplot is the aesthetic mapping. So this is exactly equivalent to what we had before. Now we are finally ready to make this into a real graph, and in order to do so we need to add one more thing to this plot, namely how we want to display our data. And when I say add to this plot, I mean that very literally, because the syntax of doing so is with the plus symbol. Notice that after the ggplot function we have the plus symbol, and that is followed by something that is called geom_point. The geom in this name is short for geometry, and what that means is that it controls how the data are displayed. So the ggplot package has various geom functions in it, and all of them follow the same pattern of starting with a geom and then an underscore and then some name. And this one happens to be the geom_point function. We'll see several others in this particular lesson already. But here, let us focus on geom_point. So geom_point is a function that creates what is called a scatter plot. A scatter plot is exactly what you can see on the screen. And it is a very simple idea. All we do is that we display every row in the original dataset by a single point. So notice that in the aesthetic mappings we have defined x as coming from the column size and y as coming from the column shape. So we know for every row what the x and y coordinates should be, and therefore we simply display each row as a single point in this scatter plot. So in this plot, every point corresponds to one unique row in the original data. Before moving on, let us talk about one more very important aesthetic mapping. So up to this point, we've only discussed the two most basic of basic aesthetic mappings, namely what goes along the x-axis and what goes along the y-axis on a graph. But there is a third, almost equally elementary aesthetic mapping that comes up all the time, namely the color of the geometric objects that we are displaying. In our case, the geometric objects are points. That's why we use the geom_point function, and therefore the color aesthetic governs what color those points should be displayed in. In our case, let us remember that the entries of the habitat column can be one of two values, arid or humid, and all that means is simply whether the corresponding snail individual was sampled from the arid or the humid regions of Floriana Island. And with that coloring, you can already see the beginnings of some patterns forming here. For example, you can see that only those individuals have a very large shape parameter that are in the arid regions, and conversely, only those individuals have very large shells that are in the humid regions. Now, this kind of information is immediately obvious from a graph like this, and it would have been very difficult to intuit something like this simply looking at the tabular format of the original data. Alright, so just to review what we have been doing so far. The anatomy of a ggplot is as follows. We have to specify three things. The data to be plotted, which is the snail's tibble in our case. The aesthetic mappings, which define things like what do we want to plot along the x-axis, what do we want to plot along the y-axis, what do we want the colors to be defined by, etc. And all of these aesthetic properties are governed by various columns of the data that we feed in this case the snail's dataset. And finally, we have to define the geometry, which tells us the way in which we want to display the dataset. For example, here we have used geom_point, which creates a so-called scatter plot, which just displays every row in the data as a single point along the coordinate system defined by our graph. One word of warning. As mentioned, when we write down the ggplot function, we continue from there by writing down the plus symbol and adding on various extra components to the plot, such as the geometry. So this is something to remember, because if we're a bit absent-minded, it is easy to revert back to our habit of using the pipe operator. Unfortunately, writing the pipe does not work. If we try to write down the pipe instead of the plus symbol, we get an error message, and it's kind of a helpful error message, fortunately. As you see in the last line of that error message, did you maybe use the pipe operator instead of the plus symbol? That's what you will see if you make this mistake, so then you can just fix it. Incidentally, the reason for this behavior is purely historical. It has to do with the fact that the ggplot package is quite old. In fact, it's older than any of the rest of the tidyverse, and the pipe operator was simply not in existence at the time when the ggplot package was developed. So because of that, there is this unfortunate historical artifact that instead of using the pipe inside the ggplot workflow, we have to use the plus symbol. It's a little bit annoying, but again, no big deal, because if ever we go wrong, we get an error message, and that will allow us to quickly remediate the mistake, replace the pipe with the plus symbol, and then everything will work just as expected. With that, let us discuss a couple more of the geometries that are built into ggplot. So up to this point, we've only seen one of them, namely geom_point, which creates scatter plots. Now we're going to be discussing histograms, and you might already know what histograms are, in which case great, but nevertheless I am going to go over that in detail and tell you right now what actually histograms are. So in order to explain the idea, let us first focus on the bottom part of this plot, namely the one with the dots in it. So all we're displaying here are the shapes of the various snails. So every point corresponds to one snail individual, and the point is positioned wherever its shape parameter or shape measurement actually falls in the dataset. So you can see that the data are more dense in some regions than others. So for example, around a shape value of 0, there are lots of points huddled up, whereas shapes larger than 0.1 or smaller than -0.1 are relatively rare. A histogram is supposed to visually express the denseness or sparseness of the data in a convenient way. In particular, now let's take a look at the top part of this graph. So what we do first is divide up the shape axis into equally sized little segments. And these segments we will be calling bins. So one bin is one of these small segments, which you can see are clearly delineated from one another, and you can see that they are of exactly equal width. So after dividing up the x-axis into these equally sized bins, the height of each of them is simply equal to the number of observations that fall in between the limits of each of the boxes. So let's take an example. Let's look at the leftmost bin. The leftmost bin has a height of about 3 or so. In fact, we know it has to be 3 because if we compare the top graph with the bottom graph, we see that only 3 data points, the 3 leftmost ones, correspond to the confines of the limits of the leftmost bin, so therefore that height must be 3. That means that exactly 3 data points fall in that particular small little region. Conversely, if we look at the rightmost bin, that's even shorter. That actually should have a height of 1, because again, if we compare it with the actual distribution of the data below, we see that there is one single data point far off at the right end, and that is the one that is recorded by that particular bin. And conversely, if we look towards the middle, a little bit below a shape of 0, you see the tallest one of the bins. That one has a height of over 40. That means that in that particular region, more than 40 individuals have fallen. So in summary, a histogram is a very good way of visualizing the distribution of data over some single axis. And in particular, the histogram is going to be tall wherever data are dense and not tall wherever data are more sparse. Alright, so after that introduction to histograms, let us see how one can create them using ggplot. So the geometry is called geom_histogram, quite easy to remember. The obligatory aesthetic mapping that one has to have when creating a histogram is the X aesthetic, and that governs which of the columns in the table shall be summarized using the bins and the heights. So we are here doing the exact same thing as we were doing before. Let me just go back a step. So notice that along the x-axis here, we had shape. And we do not specify the y coordinate here because that's simply automatically computed in the case of a histogram, right? So we divide up the x-axis into bins, and then whatever goes on the y-axis is simply a function of how densely the data are distributed along the x-axis. Okay, so with that, what will this look like? Here is the output in ggplot. So you can see that along the x-axis we have shape. And along the y-axis we have what is called count, because it just tells us how many observations fall in each of these bins. The default number of bins is always 30. Now, that's a default, but there's nothing sacred about that, and in fact it might not work well for particular data sets. So what should decide how many bins we use? Well, the more bins we use, the smaller each individual bin is. And while that is good for showing fine detail, it might not be good for other reasons. Namely, if the bins are too thin, then the probability that any data point falls in that particular bin gets smaller and smaller, which means that we'll get more and more of what just looks like random variation across adjacent bins. You can see a little bit of that maybe on this plot, where you see that sometimes it spikes up and then seemingly goes down. That's probably not a trend. That's just the artifact of how we have chosen the number of bins. So in order to change the number of bins, that's very easy to do. The geom histogram function has an input called bins, and we set it to an integer number, and that tells us how many bins we want. So for example, if instead of the default 30 bins, we want 15 bins, all we do is set the bins argument to be equal to 15 inside geom histogram. And lo and behold, now each bin is twice as wide as it used to be, because we have halved the number of bins that we work with, and therefore, as you can see, the histogram has a much more well-groomed feel to it. It seems to show much more the actual essence of what the data are doing, rather than simple random fluctuations that just happen because the bin width has been chosen to be a little too small, and therefore there's a lot of random variation in how many data points happen to fall in one bin versus the adjacent bins. Incidentally, instead of the bins argument, it is also possible to use the bin width argument. And by defining bin width, instead of specifying how many bins we want, we specify what the width of every individual bin should be. So that is a complement to bins. We either use bins or we use bin width. If we use bins, we have to specify how many of them we want. If we use bin width, then we have to specify how wide each individual bin should be. Let us look at some of the further options that one can specify inside geom histogram. As an example, let's see how we can change the color of the plot. We've already seen that color can be added to the aesthetic mappings, but we are also familiar with the concept now that aesthetic mappings are all of those properties that are governed by the data. But here, if we just want to change the color to some constant, for example, we want a navy blue histogram, that is not something that's governed by the data. That is something that we specify independently of otherwise what kind of data go into the histogram. How can we do this? It is very easy to do. Instead of specifying color inside of the aesthetic mappings, we specify it inside geom histogram and set it to a constant character string called navy. And we're quoting navy here because this is a character string that refers to a particular color built into R. We're going to be talking about the built-in colors momentarily. For now, just accept this, that if we use this, then actually this stands for a navy blue color. Okay, so that's all well and good, but maybe not quite what you were expecting. Because by coloring the histogram, you probably thought that the whole histogram would be colored, whereas here only the outlines of the bins have been colored. Yes, that is the behavior that happens here. In order to change the filling of the bars, one has to use a different input to geom histogram, namely one that is called fill. And if we specify fill equals navy as well, then now we get a histogram where each of the bars are nicely filled up with a navy blue color. In fact, we can even go a step further and specify how solid or transparent we want the filling color to be. So that property is governed by an input called alpha. And alpha is something that ranges between 0 and 1, where 0 means fully transparent and 1 means fully solid. 1 is the default, so what you see on the screen right now is a fully solid fill. But if we change that alpha value, for example, we reduce it to 0.6, like here, then you can now see that the individual bars have become partially see-through at least. If we reduce the alpha level even further to say 0.3, like you can see here, it's even more see-through. And if we reduce it all the way down to 0, then you can see that it's completely transparent. So now only the outlines are visible, otherwise the filling is not. So as I mentioned, I'm going to now tell you what kind of colors are available in R, namely apart from the navy color that we were talking about, what other names are there. In order to see a full list, we can enter the colors function in R, and then we get back a vector of character strings of many hundreds of entries long, each entry corresponding to one particular name of a color that is legal to use in R, and each of them are different. If we actually want to see what those colors look like, we can go to a website, namely this one, where you can take a nice look and see what those colors actually look like. Incidentally, I'm going to mention another sort of a cheat sheet for colors that was created by NCS, that is the National Center for Ecological Analysis and Synthesis in California, United States. So this cheat sheet both has a color chart as well as other useful information about colors in R in general, so I encourage you to check this out. Let us move on and learn about yet another geometry. So far we've looked at geom point, which creates scatter plots, and geom histogram, which creates histograms. Next up is box plots. So let us take a look at what box plots are. So a box plot can be conceived of as an even more compact and even more simplified version of a histogram, but it summarizes much the same information. So let's look at this graph. The middle panel is the raw data, the raw shape information of each of the snail individuals that we've seen before. The top panel is again the histogram that we again have seen before, so we understand what those two things mean. Now, in the bottom panel, we have the box plot, which again summarizes the exact same information in a slightly different manner. In particular, let's see what the box plot consists of. First of all, there is a box in the middle that we can see, and in somewhere around the middle of the box, there is this thick line going across. And then, at the ends of the boxes, there are two of these long lines reaching out. Those are, by the way, called whiskers. So when we talk about the whiskers of a box plot, now you know what we mean. Those are those long lines reaching out from the ends of the boxes. Let us see what each of these components mean. We'll begin with that thick line towards the middle of the box. that thick line separates the data into two halves. That is, exactly half of the points fall below that line and the other half fall above that line. This is also known as the median line, if you have heard that term before. If not, then now you know. So that is the median line, or in other words, the line such that exactly half the data fall below that line and exactly half fall above it. Okay, next up is the box around this median line. The box encloses exactly one half of the data, but not in a completely arbitrary way. It encloses half of the data in such a way that 25% of that half falls below the median line and 25% falls above it. And again, because it's 25 plus 25%, 50% is the total amount of data that falls inside that box. So half the data is inside the box. The other half of the data is outside the box in such a way that 1/4 of it is below and 1/4 of it is above that box line. That is what is denoted by the whiskers, the thin horizontal lines. So the lower whisker is the bottom 25% of the data, and the upper whisker is the top 25% of the data. So again, to review how the box plot works. The bottom 25% of the data is denoted by the first whisker up to the beginning of the box. The next 25% of the data is from the beginning of the box to the thick line denoting the median. The third 25% of all the data points is between the median line and the top of the box. And the final 25% of the data, the ones with the largest values, are from the beginning of the top of the box to the end of the whisker. So that is simple enough, but there is an extra convention that is often used in drawing these box plots that introduces an extra layer of complication. In particular, the whiskers are generally not allowed to be arbitrarily long. Instead, the maximum length that the whiskers are allowed to have is 1.5 times the width of the box. If the whiskers are longer than that, and in this particular case, for example, they are longer than that, then instead the convention is to stop drawing the whiskers at 1.5 times the width of the box. And after that, every data point that would appear is explicitly drawn out to the position where it actually belongs. And if you compare the bottom panel with the middle panel, you will see that the points that are plotted in the bottom panel are exactly those extremely large or small shape parameter values that appear in the data explicitly in the middle panel, where each of the data points are explicitly plotted. So in the box plot case, those extreme values are sort of considered outliers, and this is an easy way of judging where extremely large or extremely small values might fall. And it's important to know about this convention because ggplot, unless otherwise told, will follow this particular convention. Alright, so with that, let us create our first box plot using ggplot. We need to know the corresponding geometry, which is very conveniently just called geom_boxplot. We specify the aesthetic mappings, and just to regenerate the same kind of graph that we were looking at in the previous slide, let us set the x aesthetic to shape. So that means that we line up the shape parameters of the individual snails along the x-axis, and that's what we're going to be summarizing with the box plots. Now, that in principle would even be enough by itself, and there's no need to specify a y aesthetic. But just for fun, since we know that there are two different habitats in the dataset, why don't we specify the y aesthetic as habitat, and that means that we actually get two box plots, one for the arid and one for the humid regions. So in other words, the lower box plot that you see here summarizes all those snails that belong to the arid region, and the top one all those that belong to the humid region. And you can see at a glance that the shape parameter of those snails that are in the arid region tends to be larger than those in the humid region. Incidentally, on both this slide and the previous one, we have displayed the boxes horizontally. It is, however, a bit more common in the literature to use it the other way around, display the boxes vertically. All we need to do that is flip the aesthetics. Instead of specifying X as shape and Y as habitat, we specify X as habitat and Y as shape. So now the habitat is along the X-axis, and we see that there's arid and humid. And the shape is along the y-axis. And the fact that the box of the arid region is a bit higher up in the plot than that of the humid region is the thing that expresses that the shape parameters of the snails found in the arid region tends to be a little larger than those found in the humid region. So, as I said, this kind of way of displaying box plots is probably more common than displaying them horizontally, so it's just good to know about it. Please familiarize yourself with it, but otherwise it means exactly the same thing as displaying it the other way around. There is one more geometry that we will talk about today, and that is geom_smooth. So, let us look at this piece of code here. We start with the snails dataset. And then we define the aesthetic mappings as X equals size and Y equals shape. In other words, this is the same setup that we used in the beginning of this lesson, creating our scatter plot. And in fact, we do create a scatter plot because to this ggplot we add on geom point. So up to that point, we just create the scatter plot. But we don't stop there. We add another geometry to this that is called geom_smooth. Your first question probably is, are we allowed to do this? The answer is yes, absolutely. One can add multiple geometries to the same plot, in which case all the data are going to be displayed using all of the geometries that we specify. What does this actually look like? Here is the plot. We are not too surprised to see the points that we've seen before, because that is the effect of invoking geom point. But we see a new element that is the effect of geom smooth, namely a wiggly blue line. And what the wiggly blue line does is it tries to estimate the general trend of which direction the points are moving in. Notice also that there's this gray band around the blue line. The gray band is an estimate of the uncertainty in the position of the blue line at any one given point. Now, as it happens, this kind of wiggly line estimation of the general trends in data is not something we use very often, although it can come in handy, of course. Much more often, we're interested in a simpler linear trend, whether the data are overall decreasing or increasing. And we can do that by specifying the method argument to geom_smooth and setting it to equal to LM. And LM here stands for linear model. It is a function built into R, and if you are going to be taking the advanced course on data analysis and statistics at Linköping University, then you are going to be very familiar indeed with this particular function. But for here, do not worry about any of those details. Just remember that in order to replace the wiggly line with a straight line that estimates the overall trend, we just have to specify method equals LM inside geom_smooth. Another thing here is that often we are not too interested in that gray bar that is around the line. In order to remove it, there is an argument to geom_smooth called SE, which is short for standard error, by the way. And we can set it to false. And if we say SE equals false, then as you can see on the plot, the gray bar disappears. And instead of having the gray bar together with the line, we're only left with the line, which estimates the general linear trend in the data. Here is a question though. We've already seen that if we specify the color aesthetic to be equal to habitat, then the points in this plot will be split up based on whether they belong in the arid or the humid region. So we will have two colors. The question is, what do we have to do for the smoothing line to also split up and to separately have a line for the arid and one for the humid region? As it turns out, we do not need to do anything. If we just specify the color aesthetic as being equal to habitat, that will automatically apply to both geometries. So in other words, both geom point will be affected by that aesthetic, and you can see that because the points are now either red or turquoise, depending on whether they belong in the arid or humid regions. But also geom_smooth is affected by the habitat, by the color equals habitat aesthetic, which means that there is a separate smoothing line fit to the arid and humid regions. Incidentally, notice that this is somewhat interesting, I guess, because if we back up a step, you see that in this original graph where we fit one single line through all of the data, the slope of that line is negative, which means that in general there is a decreasing trend of shape parameter with increasing size. But we see that that's partially an illusion, because if we split those data up by habitat, then we see that although yes, in the humid region there is a decreasing trend, in the arid region that trend reverses, and in the arid region, in fact, shape increases with size. By the way, you might ask, what does one have to do if we do not want to split up our geom smooth based on habitat? So what do we do if we still want to color the points based on habitat, but the geom smooth should be just one single line, the one summarizing over all of the data? Here's a solution one can do. And in order to do this solution, we have to learn about a new concept, namely that aesthetic mappings are not necessarily specific to the plot as a whole. They can be defined locally for one given geometry. In this particular case, we want the color aesthetic to only refer to the geom point, but not to geom smooth, which means we should remove it from the general list of aesthetics and add it only to geom point. And that is perfectly legal to do, and this is how we do it. Notice that what we've changed from the previous program is that here in the ggplot function, the aesthetic mappings are only x and y, and we've removed color. Whereas in geom point, now we are defining a new aesthetic mapping called color equals habitat. So this means that the color equals habitat aesthetic is only valid for geom point, not for geom smooth. So once again, the aesthetics that we define inside the ggplot function will be valid for every geometry that we use. Whereas the aesthetic mappings that are defined inside only one of the geometries refer only to that one and not to the other ones. Therefore, since we only specified the color aesthetic in geom point, that means that the points will be split into different colors, but geom smooth is not affected by that. We get one general smoothing line across the whole dataset. Notice also that the default color of the smoothing line is this blue that you can see on the slide. If you want to override it, it is possible to do so. How to do that? In exactly the same way that how we have done so with geom histogram, if you remember. So inside geom smooth, we are allowed to specify the color property, and we just say, for example, color equals black, and in that case, we change the color to black. And notice that this color is not part of the aesthetic mappings. Again, why? Because we do not want the color to be governed by the data. We want it to be just a constant thing that we specify, in this case, black. Final topic for today, saving plots to disk. So let us generate the exact same graph that we've done in the previous slide. The only difference here is that we are assigning it to a variable. Yes, that is perfectly legal. Plots can be assigned to variables. So in this case, we are assigning the result of this plotting to the variable p. Once we do that, we can do various things with it. For example, we can display the plot, and there are two alternative ways of doing so. One is to call print p, or alternatively we can call show p. Both of them will simply display the graph. Alright, now that we have assigned the plot to a variable, we are ready to save it. And here is the syntax for saving a plot. The function that will do so is called ggsave, and it takes the following inputs. The first input is the name of the file that we want to save the plot in. So for example, if we want the file to be called graph.pdf, then that is what we have to specify as a character string, importantly. The extension matters because if we specify the name of the file as .pdf, for example, that means that yes, indeed, the graph will be saved in PDF format. Okay, so that's the first input. The second input to the function is called plot, and that is where we specify the variable containing the graph that we want to actually save. So for example, if we want to save the contents of the variable p, then we specify plot equals p. finally, there is the width and the height parameter. And the larger these are, the wider/taller the graphs are. As a bit of a strange feature here, as a bit of a strange feature, actually, as it happens, it's not just the raw width and height of the plot that changes, but also the relative sizes of the label sizes and font sizes on the graphs. So it can take a little bit of playing around with the width and height parameters to get sort of the perfect plot, one that has plenty of space in it, but also the labels are large enough to be able to be read. So you can experiment with the parameters for every given plot to find the ideal setup, but you can do so with the width and height parameters. By the way, it is possible to omit the plot argument to the ggsave function. If we omit it, then by definition, the most recent graph that was generated is the one that is going to be saved. So if we're okay with that, then we do not need to specify the plot argument. Otherwise, if we want to save something that we've generated earlier, then we have to assign it to a variable and do what we've done in the previous slide. And finally, we do not have to save graphs in, for example, PDF format. We can save them in other formats. If we want to save it in PNG format, for example, then all we have to do is change the extension to the file. Instead of using .pdf in the file name, we use .png, and lo and behold, the file is going to be saved in PNG format. By the way, if I may say so, I would say that in scientific plotting, most generally, PDF is probably the default go-to format that one should operate with. Why is that? Well, as it happens, a PDF image is not really an image file in the classical sense. Instead, a PDF file is a set of instructions for creating a picture. So, for example, a PDF file will not contain the actual pixel layout of a graph. Instead, it will contain instructions like put a dot at this and this coordinate, or draw a line between these and these pairs of coordinates. So that means that one can reconstruct the graph based on these instructions, and therefore one can make these graphs arbitrarily scalable. So a PDF can be zoomed into arbitrarily well. Whereas if we save the pictures in some sort of raster format that saves the pixels of an image, like in a PNG file, then if we zoom in too much, then the image will start getting more and more pixelated, and that can sometimes be a disadvantage. So I would say that all other things equal, it is best to default to PDF formats, although it is true that PNG also has its uses. Alright, so this was quite a long lesson, but we have covered a lot of important ground, so thank you very much for your attention, and we will continue next time around discussing more ggplot options. So until then, see you next time.